My name is Daniel Lebrero, and we are here today to talk about stability patterns. Before we get started, very briefly about myself. I have been working on the JVM for 17 years. I have built all kinds of systems, from embedded systems to big data applications. And right now I'm working as a technical architect for IG. IG is the world leader on spread betting and CFDs. It's part of the FTSE 250, and it has development centers in London, Krakow, and Bangalore. So let's talk about stability patterns. What are they? In the released book, Michael Nygaard explains 8 patterns that are going to help us to keep our applications up and running for very long, even in the case of failures. Of course, if there are failures, it doesn't mean that we need to have the same level of functionality, but we should be able to cope with those failures. How many people have read this book? A couple of guys say, okay, cool. So this is a book that I would recommend. It's one of the mandatory books as a software developer that you should read. So what we are going to do in this session is going to go through each of the patterns in the book and see how we apply it into one of IG's projects. So the project that we are going to talk about, it's called Market Analysis, or MA for short. That is a web application that what it does, it provides a bunch of information related to a market so our clients can make an informed decision before placing a trade. So to build that page, what services we need to talk with. So the first service that we need to talk with is single sign-on. So the first thing that we need to know if the user is logged in or not, and which user it is. Then we have to talk with the user preference service to know which modules, which widgets we need to load for that user. Then the header comes from the CMS, and there are some news and analysis articles that come also from the CMS. Then to show the name of the markets and the translations, we contact a service called Market Taxonomy. That piece of information comes from the client information service. That bit comes from the dealing API, and so on, and so on, and so on. So to be able to build this page, we need to integrate with 13 services. Apart from these services, we also have a dependency with other services in different pages. So why I'm talking about dependencies? Because integration points are the #1 killer of systems. When we build market analysis, we have those 2 key principles in mind. First, we want to show all the data once the page is loaded. Because first, UX told us that it was a very bad user experience to show spinning GIFs. And the second one is because market analysis is part of the public website. So we want Google to find as much data, to see as much data as possible. And the second key principle is that we think that no service should be essential. So what does that mean? That if all those services, the one marked in red, are not working for whatever reason, we should still be able to serve some kind of data. Not the prettiest one, but at least the client can see as much as it has. Very briefly, very high level, this is the architecture of market analysis. So we have a load balancer that we will forward the request to one of the market analysis instances, and then market analysis will contact a bunch of internal services. Some of those internal services will need to go to a third party to retrieve that data. If we look at our request, how our request looks like, what we do is we parallelize each of those modules, each of the widgets. We will parallelize, we'll create a task and parallelize that work. And then after those tasks have been finished, we will collect all the data and we send it to the client. And notice that for some of those widgets, it's not as simple proxying and hitting one internal service. For some of those widgets, we actually have to hit more than one backend service. So let's start talking about the first of the patterns, timeouts. The premise of the timeout pattern is very simple. You should never, ever wait for a service, for an operation to complete. You should never wait forever. So any time that a thread is going to do an operation that can block, you should be very explicit about the amount of time that you want that operation to take at most. That means that you also have to deal with possible timeout errors. So let's see how we have used this pattern in our case. In the first place that we use this pattern is when we parallelize the work. So when we create those tasks and we run them in parallel, The main thread, the Tomcat thread, what it does is going to wait a maximum amount of time. So if the tasks finish within milliseconds, the Tomcat thread will just get the data and send it straight away. But if any of the tasks take longer than that time, what the Tomcat thread will do is cancel any unfinished task and collect as much information as it can and send that to the client. The second place that we use timeouts is on the HTTP client, yeah? Whenever you make an HTTP call. So in our case, in most of the places, we use Apache HTTP client. You have to always configure these 3 timeouts on the HTTP client. The first one, the connection pool, it's how long you are willing to wait for a connection to be available. The second one, the connection timeout, is how long you want to wait for that socket to be open. And the third one, the socket timeout, it's how long you are willing to wait for the server to give back you some data. So if you configure your HTTP client with those 3 timeouts, so 1 second, 1 second, and 1 second, how long do you guys think, on the worst case scenario, the thread will be blocked? So if the server that you are talking with behaves something like that, so if it sends 1 byte every 500 milliseconds, what will happen is that the socket timeout will be reset, will start again from scratch every time that you receive one of those bytes, which means that in theory, your request can take several minutes. To avoid this, what you have to do is manually interrupt the thread doing the I/O, or in the case, if you are using Apache 4.3 or above, it comes with a future request execution service that what it will do is wrap any HTTP call in a future, so you can cancel that future when it's not needed. In other places of the application, we are actually using the async HTTP client. The first difference between the async HTTP client and the Apache HTTP client is that the async HTTP client doesn't have a connection timeout. Sorry, a connection pool timeout. So it will never wait for a connection to be available on the pool. Now, if you configure the async HTTP client exactly the same way, you will get the same behavior. Yeah? So in theory, it can take forever. But the async HTTP client, it comes with a third timeout parameter, that is the request timeout, that it will do what you will expect. So it will bound the amount of time that a request can take. If we are talking about sockets, whenever you talk with your database, it doesn't matter which kind of database it is, you will always have to think about all those 3 timeouts. The last place that you need to think about timeouts is whenever you do a lock. So all the locking primitives in Java, they will have a time version, so you should always think about using those. And if you are using queues, it's the same. Whenever you try to put, or you try to get from a queue, you have to think about using the time version. The second pattern is the circuit breaker pattern. The idea behind this pattern is that if you know that operation that you are about to execute is going to fail, it's actually better not to even try to execute it. And more if you know that detecting that failure is going to take some time. So the way you use circuit breakers is that you will wrap the operation that is dangerous in a circuit breaker. And a circuit breaker is just a state machine. So it starts in a closed state, where and the operation will always be executed. And what the circuit breaker will do is collect stats, collect information about how many times that operation failed. When it detects that there are too many errors on that operation, it will move to the open state. When it's in the open state, what the circuit breaker will do is we will not bother to run the operation, and it will return an immediate error. Then, after several minutes, depending on how you have configured it, the circuit breaker will go to a half-open state. In the half-open state, what the circuit breaker will do is try with one thread to see if that operation is healthy again. If that test fails, it will go back to the open state, and then it will again wait several minutes before trying again. If the operation succeeds, it will go back to the closed state, and everything will be fine. The way you detect too many errors, what does actually too many errors mean? It depends on which library you are using for your circuit breakers. So it can be as simple as counting the number of consecutive errors. or it can be as complex as looking at the percentile of requests fail on a time rolling window. So we use circuit breakers around any HTTP call that we make. That way, we are protecting our application from a slow service. We have one circuit breaker for each of those internal services that we call. Now we have found in production that just using one circuit breaker per service is a little bit too coarse-grained, because in the same service, sometimes the URLs that you hit, they have completely different performance characteristics. So that means that they are just too coarse-grained, and we should be using one circuit breaker per URL, or maybe it means that our services are not micro enough. Whenever a circuit opens, we don't alert immediately. So what we do is usually wait between 15 minutes and 1 hour, depending how critical is the backend service, before raising the alert. And the usual, the most famous library in Java is the Netflix histories. The next pattern is the bulkheads. The idea behind bulkheads is that when failure happens, when there is some error in your system, you want to somehow limit the damage that failure can cause. And the premise is that you are always going to find failure. So even if it doesn't matter how much do you test or how much resilience you try to put into your system, failure is always going to happen. The idea of bulkheads, it comes from the shipping industry. So the ships are actually divided in compartments, with the idea that if there is some damage on the hull, just one of those compartments will be flooded, and the others will not, so the ship will still remain afloat. So let's see how we use this. In the very, very small, what we do is we have one HTTP client for each of the backend services that we are contacting. That way, if the connection pool is not shared between the different services. So if something goes bad within one of those backend services, we are sure that we don't affect the communication with the others. In the very, very large, we have divided our clients into 2 groups, and we have different data centers for each of those groups. That way, if something bad happens on the demo data center, our live clients will not be affected. And we have something in the middle between the two. So when we started moving all of our services to Tomcats, we started by putting several applications in the same Tomcat. And that was because we didn't want to pay the overhead having one JVM for each application. But we really quickly find out that doing this, it will mean that an error in one application can affect other applications. So for example, if application number 2 starts to have a memory leak, it will also affect application 1 and application 3. So what we end up doing is having one Tomcat for each application. That way, what you are doing is you are isolating the memory. So the memory usage of one application cannot affect the memory usage of another application. We are also isolating the class path, database connections, and the Tomcat thread pool. Also, if you need to deploy a new version of the application, or if you need to restart one application, again, you are just affecting that one particular application. Now, because we are still running everything in a Linux in the same box, that still means that we have some shared resources. So CPU and I/O, it's something that still one application can affect another. The steady state pattern. Steady state pattern, it says that for every mechanism that accumulates a resource, there should be another mechanism that recycles that resource at the same pace or a faster pace, with the idea that no resource is infinite. So you just think about garbage collection, right? If you are accumulating, if you are creating too many objects and your GC is not able to keep up, what you end up is with a completely unstable system. So from the book, it comes with these examples. So the first one is log rotation, that I think we all by now do. But then you have to think about, for example, to limit always the cache, the size of your caches. And it's the same with any connection pool. You have to limit how many connections you want to have against the other system. That archiving and purging, so to keep your database queries snappy. And if you provide an API, if you are providing any pagination on that API, you are applying this pattern. Because what you are doing is, again, limiting how much data you need to process and how much data you need to send. Now, the other place that you need to apply this pattern, it's with thread pools. And I want to focus on thread pools because in the interviews to senior developers that I do, I always ask a question, and I usually don't get the answer that I expect. So the question is, if you have a thread pool in your application and you want it to be production ready, what things you need to configure in that thread pool? So everybody knows, everybody is right, that you need to configure how many threads, the maximum number of threads on that thread pool. Some people also know that you can configure the minimum number of threads that you want to have. And even some people know that you have this thing about the idle time, so how long a thread can be idle before you actually stop it. But these are not the things that I'm looking for. The thing that I'm looking for is that whenever you create a thread pool, the thread pool always comes with a working queue. And if you don't configure a working queue, what will happen is that you will get an unbounded working queue, which means that we are violating the steady state, because an unbounded queue means that you can have an infinite amount of tasks there. So first thing, you can run on an out-of-memory error. But the other thing is that if you have 10,000 items in a queue, you probably are working on the first ones, which probably by the time that you get to work on them, the client has already disappeared and is actually not interested on the results anymore. So you're wasting time. But now that you have a working queue and you have to put you bound so you have a maximum size, the other thing that you need to think about is the rejection policy. Yeah, so what do you want to do when that queue becomes full? So the JVM comes with 4 rejection policies. The one that we are using usually is the abort policy, which means that when you try to put an item into the queue, you will get straight away an exception. And we want that because we want to write an alert as soon as that thing happens. The next pattern is called the fail fast. So in the case of the circuit breaker pattern, what happens is that the client tries to guess if the server is going to fail, given the historical behavior of the server. In the case of the fail fast pattern, it is the server itself, the one that it will check before doing any work, if he's going to be able to fulfill the request. And the idea is that if you are going to fail, it's better to fail as early as possible instead of spending the time and resources just to find midway through that you are missing or that a circuit breaker is open. So from the book, things that you should check as soon as possible is that if you are going to fulfill your SLA, you can check if the circuit breakers, the state of the circuit breakers, that for the request that you're going to need. You can reserve resources, so memory or connections from the connection pool, and validating the user input. Now, from all these 4 things, we actually just do the last one, because at least in our design, we didn't find a really easy way to be able to do all these things, because we have all that parallelization, and everything was just too dynamic. So basically, we don't use this pattern at all. The next pattern is handshaking. Handshaking is very simple. What you are trying to do is that it says that the client should contact with the server to know if he's going to be ready to serve the request. A couple of examples from the book that we use. It's whenever you get a connection from the connection pool, a database connection, usually do some kind of simple query to check the health of that connection. Or if you have any kind of heartbeat mechanism, it's another way of doing this handshaking. Now, in our case, we also have an additional one that is market analysis. The application that we're talking about is actually fronted by Varnish. If you don't know what is Varnish, Varnish is just a HTTP cache, a proxy. So you can configure Varnish to hit some health point in your application. And whenever a request comes, Varnish will check if the application is ready, given that background check. And if the application is ready, it will just forward the request. And if the application is not ready, it will return the last cache result, or an error if the request has not been cached before. Test harness. So this is probably my favorite one. Test harness just tells you that whenever you do testing, you should expect the worst, and you should behave the worst. So you should be really, really evil and really, really mean with your application. And when it says evil and mean, it gives you some examples that you will usually not think about. So these are some examples from the book. So for example, if you talk with an HTTP endpoint or with some kind of any socket, it tells you to accept the connections but never send any data. Or read or write the request at 1 byte per second. Or return huge or infinite responses. So something that you usually don't think about. The way we apply this pattern is that in our build plan, in our Maven project, what we do is we use the Maven cargo plugin to start a Tomcat, and we start the whole application in that Tomcat. Then, from our test, we start an embedded Jetty with some evil servlet configure. And then from the test, we will hit externally the market analysis application, and we will configure the market analysis applications to point back to that evil servlet. That evil servlet, how it looks like, it will be something like this. So it's the same example, the same code that I showed before. Now, if we, in the new projects, instead of building things by hand, there is a wiremock library that it will give you this functionality by free. So with this way of testing, we are able, with this kind of testing, we are able to test most of the stuff. But in the newer projects, because we want to be even more able, what we are actually doing is we are actually using Docker to test the resilience of the application. So it will look something like this. We will start a market analysis container or several of them if you care about the clustering of your your clustering logic. Then we will install a toxic proxy container. So toxic proxy is a container from Shopify, I think, that it allows you to configure. It's a TCP proxy, so it allows you to configure faults at the TCP level, so delay packages or do anything that you want with the TCP. And again, we'll do the same test. Through the external interface, we will test the application. Using Docker, we have found that we can test all the cases, but if you put a little bit of extra effort, you can also do things like crashing processes or pausing them, or even testing slow disks. There is a library called Archelian Q, which gives you a DSL on top of Toxic Proxy to be able to configure and to use it on your test. The last pattern, it's decoupling middleware. So the usual example, it's to use a UMS queue. So instead of having a synchronous request response, to use just some message. Now in our application, because we are basically just trying to build a page, we thought that we will not be able to use this pattern. But the idea behind the decoupling is that what we are trying to do is somehow decouple the resources that we are using from any kind of external influence. So if we look at the request, a typical request from the user, it will go through market analysis. Then market analysis will forward that request into to an internal service, for example, the news service. And then the news contacts a third party, so it goes through all the internet, and then the request will come back. That means that our Tomcat thread is being stuck there, waiting for as long as the third party wants. So we wanted to avoid, that coupling between the thread and the third party. So the first version of most of the internal services, we follow this pattern. We'll just put a cache there in the middle with some time to live, so that if when the client came, hopefully the item will be in the cache. So the time that the thread has to be, it's their block, it will be as small as possible. Now, when we deploy this into production, we found that this was the case. So most of the requests will be very fast, but then there will be a very long tail of requests that will hit the worst case, either because the item was not in the cache, or because the time to live has expired, so you have to go and fetch the fresh value. So in the second version of all those internal services, we follow a different pattern. What we did is create some kind of background process that will pull the data from the third party and will store it in some kind of local storage. And then we will expect that our market analysis thread will always hit that local storage. So it gives us back control about that local storage. It will give us control about how, if we need to tweak anything. When I say local storage, it can be as simple as a hash map, a memory hash map, or it can be an Elasticsearch cluster, or it can be your own database. And when I say pulling data from the third party, it can be as simple or as silly as some FTP files, so getting FTP files from that third party, or HTTP pooling, or HTTP pipelining. Now, the problem with this pattern is that sometimes you are duplicating the functionality given you by the third party. Yeah? So search on some things you need to duplicate all that logic in your service. So this gives us the decoupling between that Tomcat thread versus hitting the third party. In fact, we like this pattern so much that in market analysis itself, what we look at were all the things, all the data that it was actually critical to be able to show the minimum page. So for example, that header that I mentioned at the beginning, the top header, that will come from the CMS. But of course, if the CMS was slow or down, we actually want to still be able to show the page. So what we will do is have a background process that will get all the pieces of information that were critical for our application, and we will just put them in memory. There was one particular case where we couldn't follow this pattern because the third party didn't provide any kind of API that will allow us to pull all the data, plus all the data that we need to pull, it will be just huge. So what we did to decouple the threads will be something like this. The client will make a request that it will hit that cache. If the element was not in the cache, what we will do is we'll put that work about going and fetching the data to the third party into a queue. And what we will do is return a response telling the client, oh, please, can you come back in 10 seconds, because maybe by that time I have had time to go and fetch the data from there. And the hope, as I said, it was that the thread, the thread pool that we have there, it will have time to fetch the data and put it into the cache before the client came back again. So here we are bending a little bit the key principle of having all the data on load, but we are doing best effort, which means that if the element is in the cache, we will draw it straight away. But if it's not in the cache, we prefer just not to block the whole application. The last pattern, the last way of applying this decoupling pattern is if you use any kind of async I/O. So when a request comes into your Tomcat, there is a thread pool, the Tomcat thread pool, that is the one that takes care of executing that request. So traditionally, when you go and have to hit a third party, that thread will block until the response to that third party, to that internal service, will come back. But in the case if you are using async I/O, what will happen is that when you get to the point of actually sending the request to the third party, instead of waiting, that thread will go back into your pool. So that thread is ready to be able to execute other requests. Then at some point, when the response comes back, there will be another thread pool, in our case, the async HTTP thread pool, that will get that data and will be finished processing the request and send the data to the client. So if you look at it, the idea is that, again, the amount of time that the thread is blocked is very, very small. And if you look at that, it's during that time, there is no threads. There are no threads really waiting for the I/O to happen. So this is where the scalability of all the async I/O comes from. So some references about libraries that I have talked about. And in summary, never wait forever. Don't do it if it hurts. Contain damage. Nothing is infinite. Don't waste your time. Agree before doing. Avoid waiting. And please be very evil. And with that, I'm happy to take questions.